Hello, everybody. How are you doing today? Okay, in this video, we are going to talk about something called integration by parts, as you can see. So this all came about when mathematicians were like, whoa, that's way too big. Come on now. When mathematicians were like, hey, I want to integrate this, but how the heck do I do it? So what they thought about was, well, it kind of looks like the multiplication of two things, right? So like x and then ln of x dx, or maybe I do x dx and ln of x, right? But essentially, this is like the multiplication of kind of two different functions. One's linear, one's natural log. So mathematicians always try to think about the tools in their bag. And the only thing that we know about calculus related that's like the multiplication of functions is if I were to do the derivative, say of two different functions, u and v, in terms of x, well, that would be u v prime plus u prime v, right? So the derivative of the one and derivative of the other, multiply them, right? This is our product rule for derivatives. Well, if they're trying to do the integration, what they thought about next, well, hey, if I do the integral of the entire thing, or take the antiderivative of the entire thing, over here on my left side, the integral of the derivative is just the thing itself, so just uv, and then I would have the integral of u, I'm going to write this as dv, right, the derivative of v, plus the integral of v times the derivative of u. Well, we're kind of close, but the thing that kind of sucks here is I have two integrals instead of just one. So what they did is they decided to rewrite this, and there's no rhyme or reason why they did what they did here, but they subtracted over the v du such that I have one integral by itself. So this will be the integral of u dv equals uv minus the integral of v du. So they said, hey, this is cool because now I have some function u and some derivative of v multiplied together within that integral. So let's use this fact and see if I can get there a little bit more easily now. So really what I need to pick is I need to pick what is u and what is dv, and then I can equate it to this information over here. So let's go back to this. All right, so it was integral of u dv equals uv minus the integral of v du. uv minus v du. This is something that I have memorized, uv minus v du. So let's pick a u and see what happens. Let's let u be x, right, because it's the first thing, and dv be ln of x dx. So I will need a du, right? So looking at u, du is just the derivative of x, which is dx. And I will also need a v. I'll need a v twice. The issue here is that I do not know the antiderivative. Since I'm going from dv backwards to v, I do not know the antiderivative of natural log. So let's rethink this. Let's create a new u and dv. So let's let the u be ln of x, because then my du would be 1 over x dx, because the derivative of natural log is just 1 over x, right? And then my dv then would be x dx. And the antiderivative of x is x squared over 2. So it looks like I have all my parts. So let's equate this to the other side. Right? And just to help you kind of see this a little bit more easily, my u is right here, and my dv was all of this right there. So notice everything in my integral, my initial integral, is taken care of. They're all covered as far as I am showing where I am substituting everything. And notice that I have my dx notation, I have my dx notation. Be very careful of notation. They're going to be super looking at all of that stuff as well. So I want to make sure that you take note of it too. So let's do this. All right, so uv, So u is ln of x, and v is x squared over 2, minus the integral of v du. V is x squared over 2, and du is times 1 over x dx. And notice, please, too, this is another reason why I write that dx, because I don't want to forget to write it. If you write an integral, you need to have a variable of integration. If you don't, it means nothing to us. So now this is workable, right? So I'm going to rewrite the first one because it's really just x squared times ln of x over 2, right? I could have left it like this as well, but this is probably how they will write it on a multiple choice. Now I'm going to simplify here, right? I have a 1/2 that I can factor out. The x squared over x will divide to make 1x. So I have minus 1/2 integral of x dx, which I know I can do because I already did it. Yes, sir. So I have x squared ln of x over 2 minus 1/2 x squared over 2 plus c. And I can leave my answer like that. I could also rewrite this as like minus x squared over 4. But the big thing that I was trying to show you guys is now I'm able to do that integral. And that's what it is. So the integration by parts rule allows us to do the multiplication of two different parts within an integral. This is not my first go-to. If I could choose u substitution instead of that, I'm going to do u substitution every time. So this is not like a one-size-fits-all. This isn't going to apply to all integrals. Just make sure you are thinking about this. All right. Integrate the following. So I will have to choose a u, right? So I notice, first thing, this is something times something, right? So I'm going to let u be x, and that means dv is what I have left. Sine of x over 2 dx. And I don't think it matters in this case which one you choose as far as what your u is and what your dv is. I think you could have done u as sine of x over 2. I am picking u specifically to be this for something that I'm going to show you in just a minute. It's going to be a shortcut method for this. So, du, the other thing that's nice is that du is now just dx, so I know I'm not going to have to worry about any like simplification or anything. V here would be, let's see, negative 2 cosine of x over 2. Right, I'm doing an antiderivative. Please remember this is an antiderivative. So if I think about this, the derivative of cosine is negative sine, and I would have to do the chain rule here for the 1/2, right? So the derivative of this, let me do it in a different color, right? dv, if I do it straight like this, say I ignore that negative 2, would be negative 1/2 sine of x over 2. But notice, right, this negative 1/2 is not there. So since it is not there, I must have multiplied by that negative 2 out front, so that if I put it there, now I have positive sine of x over 2 as my derivative of that. So this is really just doing a u substitution where you are letting u be x over 2, and then du is 1/2 dx, right? But the more that you can think about this u substitution, this antiderivative in your head, the better off you will be, I promise. It's something you really got to get used to if you're going to be in BC and moving forward. All right, so now I have my u and my v. So let's go ahead and throw this out there. So this equals uv, so negative 2x cosine of x over 2 minus the integral. But if I have a negative 2, right, so it's minus the integral of du, or v du, right? So then I see that I'm going to have a negative 2, so I'm actually going to factor that out and make this plus 2, the integral of cosine of x over 2 dx, which we can do the antiderivative of cosine. So this becomes negative 2x cosine of x over 2. Let's see, the antiderivative of cosine is sine. I would have to multiply by another 2, so plus 4 sine of x over 2, and plus c since I have an indefinite integral. And that's it. That's all there is to this problem. So the shortcut way is called tabular method. This will only work in certain situations. but it can definitely make our life a lot easier if we can use it. So the tabular method will only works if, let me pause. Okay, so this only works if the derivatives of u eventually go to 0. The other thing that has to be true is I need to be able to take the antiderivative of v as well, of dv. Right? I got to be able to go backwards with dv in order to make that work. So this case is cool, right? Because we did it. I did it such that u was x and dv was sines because I wanted to be able to set up tabular as well. And this is a tabular method, right? So if I have alternating signs is my first column, I'll do that bit last. I have a u column and I have to select a dv. So still I'm having to pick a u, I'm having to pick a dv. If it helps you make columns for this stuff, I usually don't. But this is kind of a table. You have to imagine it's a table. So my u in my integral, the thing that is eventually going to go to 0 is the x. So that means dv will have to be my sine of x over 2. So u is x and dv is sine of x over 2. I'm going to do the u column until my derivative is 0. So the derivative of x is 1, the derivative of 1 is 0. Then I have to do my dv column as many times as I did my u column so that I have the antiderivatives. Just don't forget that this is the antiderivatives, right? So derivatives, and going down, this is the antiderivative. Yeah, sorry, that's really poor writing. But that's the antiderivatives, right? So this will be negative 2 cosine of x over 2. And then I would have negative, let me write that in line better, negative 4 sine of x over 2. Move this just a little bit. Okay, and then the alternating signs, you always start on positive. And then each column you go down, you literally just alternate the signs. So plus, minus, plus. As many times as you need to, you are just alternating the signs as you go on forever. Forever and ever. Okay, so now looking at this, I know this is the correct answer. But how did I come up with that? Well, let's see, my first term was negative 2x cosine of x over 2. So it looks like negative 2x, right? So these two are kind of connected. Cosine of x over 2, right? So that comes in good. And then 4 sine of x over 2. Well, there's a 4 sine of x over 2. So maybe it follows the same pattern that I multiplied by 1. And if that's positive, it must have multiplied with negative. So there's really your pattern right there, right? It goes over. Let me erase all of this. Right, so to create that first term, it goes across and then, oh man, I didn't want that to happen. Across, down, to get your next term. So you multiply those straight across to get each term in succession, and then plus a c if you have an indefinite interval. Again, this is called the tabular method. What you have to have, you must label, right? You must label what you are doing in each column, alternating signs, u and dv. I'm not looking for you to call it like tabular method. You can if you want to, right? But it needs to be organized. If it's not organized, you're not going to receive credit for doing the tabular method. This is a completely fine way to do the free response. You will see them often do it in free response if it is available. And it is available on the next one, right? Because I need to, so looking at the next problem, right, I have two functions multiplied together. I have an x cubed and e to the 2x. So I'm going to need to do integration by parts here. So do I have a u that eventually goes to 0? Yeah, I got x cubed. Do I have a dv then that I can do the antiderivative? Yeah, I got e to the 2x. I can do the antiderivative of that. So let's go ahead and set it up, right? So I'll have alternating signs. I have a u column and a dv column. So my u, I'm going to choose to be x cubed. dv then will have to be e to the 2x. And notice on these two, the question was asked sometimes, do I have to have a dx there? No, you don't have to have a dx. They're not specifically looking for that because you are explicitly doing the antiderivatives there as you go. So that will take care of itself. Do I need a dx here? No, that will take care of itself as well. That's the nice thing about the tabular method. So let's work through this, right? So I'm going to do my u as many times as I need to make that derivative 0. And then I will do my dv column as many times as I have here. So I'll need to do 1, 2, 3, 4 antiderivatives there. So this is where, again, like I said, u substitution in your head, got to be able to start getting there. So let's see. I'll have 1/2 e to the 2x, and then 1/4 e to the 2x, and then 1/8 e to the 2x, and then 1/16 e to the 2x. My alternating signs always start with a positive, and then alternate them. Right? That's why it's called alternating signs. And then for my answer, I'm going to go over, down, over, down, over, down, over, down, until I get to my 0. So this one, I will have 4 separate terms. The cool thing here about my tabular method is if I have 4 terms, that means I would have actually had to do integration by parts 3 separate times, which is wild. That is so much work. Okay, so let's write them. Right, I'll have x cubed e to the 2x over 2, and then minus 3x squared e to the 2x over 4, plus 6x e to the 2x over 8, minus 6x, no, just minus 6 e to the 2x over 16 plus c. And that would be fine for an answer. What I will tell you they will do is they will probably simplify and write that on their multiple choice. They may also factor. So I'm just going to show you the factored version, because simplifying these fractions, I hope you guys can do. 3/4, right? And what, 8? No, 3/8? No. Yes, 3/8. Ha! They may factor out a, let's see, what would it have to be? 1/8, and they will probably even do an e to the 2x, because it makes this a little bit nicer. So let's see, that would be 4x cubed minus 6x squared plus 6x minus 3 plus c. This is more than likely how they will write it on a multiple choice answer. So the nice thing about this is this creates a polynomial that we could mess with if we needed to, if we need to set this equal to 0. And also the e to the 2x is on the outside. So there's lots of reasons that it is nice to be able to do this. Okay, but that's it. That's it. That's my answer. That's all the work that I need to show for this problem. I'm done. All right, moving on. Well, here, so I do have a definite integral, so I'm not going to have a plus c at the end. And it doesn't really look like the multiplication of things, but the question that I have is, do I know the antiderivative of natural log? Well, I don't. So what we can do instead is say let u be ln of x, and then dv is just dx. The way this will work out is du is 1 over x dx, and v is just x. So this would be, let's see, uv, so x ln of x, all right, and that is evaluated from 1 to 2, minus the integral of v du. So I'm multiplying these two things. If I'm multiplying these two things, notice the x times the 1 over x will make 1. So minus the integral from 1 to 2 of v du. So 1 over x times x is just 1 dx. Then I can evaluate this part right here. So x ln of x minus just x from 1 to 2. So throw in my 2. So 2 ln of 2 minus 2 minus, throw in my 1 ln of 1 minus 1. And then we can simplify this if we wanted to. So let's see, ln of 1 is 0. That goes to nothing. So I'm minus a negative 1 here, right? Minus negative 1 is going to be plus 1. So 2 ln of 2 minus 1. And that would be my answer on a multiple choice question there. Alrighty. So sometimes it's useful to have this even if you only have really one function there. Moving on. E to the x cosine of x. I really like these. These are cool. So I do not have a u that will eventually go to 0. Right? I have e to the x and cosine x. There's two transcendental functions. That's just what e to the x and cosine are called. Trig functions, e to the x, ln, they're transcendental functions. So I'm just going to try something. I'm going to let u be cosine of x and dv be e to the x dx. The reason I chose e to the x dx as my dv is just because it's easier to do the antiderivative of that. So then my du will be negative sine of x dx, and my v is just e to the x. Beautiful. So this would be uv, so e to the x cosine x minus the integral of v du. Since I have a negative here, I'm going to go ahead and factor it out, make that a positive. V du, so e to the x sine of x dx. Well, that didn't get me really anywhere. I mean, it's kind of the same deal. It's just now sine instead of cosine. So let's just do it again. Let's just try it again. So I'm going to let my u be. I'm going to keep it consistent and do my trig function again. If you don't keep it consistent, you're actually just going to come out with 0 equals 0, and it won't really help you at all here. All right, so this is the second time I'm having to do integration by parts on this problem. So let's see, I have e to the x cosine of x plus, now I'm doing the integration by part of my integral, so uv, so e to the x sine of x minus the integral of v du, so the integral of e to the x cosine of x dx. Which, hey, I think I've seen this before, right? This is this. So the workaround here is I actually have the original equation. So if I write this, I'm going to write this in a way such that it helps you see it a little bit easier. Because until you do this, this problem is a little bit harder to make sense of. But if this is equal to e to the x cosine of x dx equals all of this junk. Oh, I forgot I was in that. Duplicate. Right? This equals all of that. So let me drop my parentheses since it's really just distributing a positive. It's not doing anything. Well, I actually have some like terms here. The like terms is actually my integral. Right? So if I add over this part right here, add it to the other side, now I will have two of those integrals equals, move. So two of those integrals equals all that stuff right there. So all I really need to do is divide everything by 2, and that's it. So I would have, technology is amazing. Love it. Me. Right, and that's it. E to the x cosine x plus e to the x sine of x over 2 plus c. That's the problem. That's the whole deal. These are called loopers or comeback kids or I don't know, something like that. Because your original integral comes back and you can add it to the other side to help you finish solving the problem. These are cool. I like those. All right. So the next thing I have is a kind of review problem for you guys. So I'm just going to run through it. The last part I will require integration by parts. But let's just go through. This is a very good example practice problem for you. Very well could show up on an AP test. These are good problems. So let's see. I'm given the derivative is given by this, for this, and I'm given an initial condition that f of 1 is 7. I'm told it has a critical point at 3. Now at this point, is it a minimum, maximum, or neither? Well, if it is a critical point, let's just know that the derivative is 0, and I can see it is 0 as well. So if we do our first derivative test, and I see how f prime relates to f around 3, let's see, if I plug in 2 or something like that to here, right, 2 minus 3 is negative 1, so the f prime would come out negative, which means f must be decreasing there. So maybe it's a minimum or neither. So let's check bigger than 3. If I plug in like 4 or something again to the f prime, that would be positive. So since I'm going up, I know that 3 has to be a minimum. So x equals 3, this is my justification statement, is a minimum, English, minimum, because f prime goes from negative to positive. Right, that's our justification. You could have also said that f goes from decreasing to increasing, but I like stating things in terms of f prime when I am given f prime. All right. On what intervals is the graph both decreasing and concave up? So I'm decreasing from 0 to 3. Notice it's for x greater than 0. So it has to be somewhere between 0 and 3. But if I'm concave up, that just means my second derivative has to be greater than 0. So let's go ahead and take our second derivative. So f double prime of x equals, let's see, 1 e to the x plus x minus 3, derivative of e to the x is just e to the x. I'm going to go ahead and factor this. 1 plus x minus 3. So this becomes e to the x, x minus 2. Right, and I really want to figure out where this equals 0. Right, because if it's concave up or concave down, it'll happen around points of inflection. It equals 0 when x equals 2. E to the x is never 0. So let's do our second derivative test, and let's see how f double prime relates to f around 2. So if I plug in 2, I'm going to think of it in this case. If I plug in 1, then 1 minus 2 is negative, so this is negative, which means I'm concave down. Bigger than 2 will be positive, which means I'm concave up. Whoa, that's ugly. Concave up, that's a little bit better. So I'm concave up, so decreasing and concave up. So I'm concave up from 2 on, and I'm decreasing from 0 to 3. Those overlap from 2 to 3, so my interval is 2 to 3 because f prime is less than 0 and f double prime is greater than 0 on that interval. That's it. That's my justification. You do need both parts. This would be worth 1, 2 points for your justification. This one is also 1, 2 points, right, for your justification. Find the value of f of 3. So let's see. What were we given? We were given f of 1. Now, I've already taught this in class, and a lot of students, when they did this, felt like they needed to take the antiderivative, have the plus c, plug in the 0.17, figure out what that c is in order to do this problem. I do need you guys to be able to recognize a different way, though. Please remember that if this is my initial position, and if I go from here, if I add the accumulation of change, or the integral, from 1 to 3 of f prime, that will give me where I end up at f of 3. All right, so just remember that the area under the curve represents displacement. The integral represents displacement. How far, not how far I travel, where I have traveled to. If I go forward and backwards, whatever I do, that will help me figure out where I've ended up. That is how I would like you to set these up. You're going to have problems that you're not going to be able to solve for that value of c. So let's see, f of 3 equals 7 plus the integral of 1, 2, 3 of f prime, which was x minus 3 e to the x dx. So I will need to do an integration by parts here, and I can do the tabular method since I have a u that goes to 0. So alternating signs, u and dv. U is x minus 3, and then I'll have 1 and 0. dv is e to the x, so e to the x, e to the x, and alternating signs. All right, so this is going to be 7 plus uv, right, so x minus 3 e to the x, and then minus e to the x, evaluated from 1 to 3. Please do pay attention to notation for all of this stuff. You lose points on bad notation, so don't lose points on bad notation if you know what you're doing. All right. And you can throw in your 3, so e cubed times 3 minus 3 is 0, right? Minus e cubed minus, now throw in 1, so e to the first negative 2 minus e. All right. You can leave it like that, right? For response, that is a complete answer. You are done. Multiple choice, you will need to simplify. So let's practice simplifying. So 7 plus, let's see, this would be negative e cubed, so I'll do minus here. E cubed. Now thinking here, this is negative, so let's do this simplification first. This is negative 2e minus e is negative 3e. With the negative, we'll make that plus 3e. That is where I will end up. Without a calculator, that is my answer. All right. Sorry this was so long, but hopefully it was informative. Good luck to all of you. If you have questions, come ask questions. There's a good luck monkey. And I'll talk to you guys soon.